Machine Learning Crash Course. Today we want to continue our discussion about dimension reduction methods, and we introduced to some new methods like Kernel Pca, SVD, and a quick introduction to ICA, or independent component analysis. But first, because the PCA itself is very important tool in machine learning, let's recap what was PCA. So the PCA tries to find the direction of maximum variances for the data. So it tries to find the direction of the data, that the data has maximum variance on those directions in a descending order. So if the data is similar like this, then the PCA as the first component recommend us this direction, and as the second direction it recommends us this direction, because we know that the PCA components and PCA directions are orthogonal to each other because they are related to the eigenvectors of correlation matrix, and the eigenvectors of this matrix are orthogonal to each other. So we know that if this is one direction, then the other direction is this one. Okay, so let's see this in Python. I wrote a quick example to see how could you do a quick PCA in here. Okay, first we import NumPy as MP to generate some random samples. Then we import Matplotlib, the pyplot to plot the data and other stuff, and then we import PCA from scalar to actually perform PCA. So in here we generate some data from multivariate Gaussian distribution. So it is the multidimensional Gaussian random variables, and as you could see in here, we have something like probably this direction would be recommended by PCA as the first component that is very beneficial for us to reduce the dimension to that component, and the second one probably would be this one. Okay, now we plot this, so we know how to plot with Matplotlib. For just discrete data, you just use O in here. Then we set the axis limits in here from -20 to 20 for both axes. Then in here we defined PCA with two components. So because in here we have just two components, we could use in here one or two. So I used two in here to see the both directions. Then we fit our transform to the data. In here you could see that I print explain variance ratio. We explain it some minutes later what is that and why is this useful for us. It is so useful actually when our data is has more dimension than 2. Okay, in here with components you could get the eigenvectors that is related to your data. So the direction, if you want to plot the directions, you could get the components, and the singular values are related to the importance of the components, or they are related to the lambdas that we saw in previous session. So, and the second norm of the components vector are 1 in here, so they have a unit norm. And as you could see in here, the singular values, one of them is 61 and another one is 20. So probably the first direction is this one, and the importance of this is 61 somehow, and the importance of this is 20. So it makes sense for us now, because this direction is more important than this one. Okay, so if we plot again the data, and in here you could see that how we plot the vectors. So because we want to plot the PCA directions in here, and yeah, you could see that how did we plot this. Okay, so we have two directions in here, and yeah, that's it. As you could see, we guessed right what are the directions that PCA recommend us that we could use to dimension reduction. Now, another question maybe you ask is probably is how to choose number of components in PCA. So let's say our data has lots of feature numbers, like 400 or thousands of feature dimensions, and you want to know how should you put the number in here. You don't know how many components do you need. For this, a typical approach is to use explained variance. So we could see how could you do that in here. Now let's say we have a data set of relating to a pulsar star. It is downloaded from Kaggle. You could download it from there, but now it is not important. So as you could see in here, we have 1, 2, 3, 4, 5, 6, 7, and 8 features per each row. So each data has 8 features, and this is also the target values or labels for each data. So we read the CSV file with pandas, and we use the min-max scaler to actually normalize the data between 0 and 1. This is very useful. So before performing PCA, try to normalize your data in using standardized method or min-max scaler or whatever you think that it is useful. Then, so in here, as you could see, we rescaled our data, and when we define the PCA without any number of components, then the output of PCA components is equivalent to the number of directions in here. The number of directions in the original dimension. So if our number of features is 2, in here I have 2 dimensions, so if I don't pass anything to the PCA, then the number of components is 2, and so on. So if I have 8 components, because in here I have 8 components, so it assumes that n is equal to 8 in this situation, and so it gives us 8 different components. Okay. Now, if we print, let us print explain variance to get some insight about it. If you print explain variance, you could see that the sum of all explained variances are 1. So it means that the general variance of data can be explained by all of the dimensions of the PCA components. But also, as you could see, the first component could explain 63% of variance of the data, and the second component could explain it is approximately 20% variance of the data. So if we plot the cumulative explained variance ratio, so it means that for the with just one component we could explain 63% of the explained variance, and so on. So when we have one, maybe it is better to shift it one to the right. So 0 in here means 1. Actually, when we have one component, we have 63 in here, and as we increase the number of our components, then we could reconstruct our data better. So it is very obvious that when we have full number of dimensions, then we could actually reconstruct our data perfectly, or explain our variance of our data perfectly. So in here, this is actually the way that used in many different methods, like in k-means. We will see that in these situations we have some knee point, maybe this point or this point. So in this point you could see that we've just 4, so this is 3 means 4 number of features, because 0 is equal to 1 number of features. So if you use 4 features, you could explain 95% variance of your data. So probably you could put 4 in here to get suitable result. So you reduce the number of your components, the number of your features, which is 8, to 4. So we halved it. So it is so probably useful for us to do that. Okay, so yeah, and now you know how to use PCA and how to choose number of components using explained variance ratio in here. So explained variance ratio is related to how much we could reconstruct our data when we use PCA. So again, if you don't know what I mean by reconstructing data, so in here, let's say these are the data, and so let's say I just use the first direction of PCA that it introduced to me. So in this situation, I have the projection of the data on this. So because this direction it has maximum variance of data, so I probably retain good variance of the data in here, but as you could see, I lose the variance in this direction. So maybe I probably retain 80% of variance and I lose 20%. So if I want to have another 20%, I should add this direction. So in this case, I will have the full description of our data. So I will have 1 as explained variance that that could be described by the number of components in here. So always when your number of components is are equal to the number of components of your original data, then you have 1, because your original space dimensions are equal to the dimensions of your PCA. So your PCA components could explain fully your data, and you when you don't reduce your dimensions, so in here I have 2 and my original space also have 2 dimensions. So in here when I have 2 dimensions, so I don't have any lose of information, so or I don't have any information loss, so I could reconstruct my data perfectly. So it means that the explained variance ratio is 1 in this situation. Now I hope that you grasp the idea behind the explained variance ratio, but if you don't, you could actually search more about that, but I hope that explanation is enough for you. Now we want to talk a little, actually really a little, about SVD, or singular value decomposition. Singular value decomposition has a very tight relation to PCA. So many of you maybe ask this question from yourself, that what is the difference between SVD and PCA, especially if you see the if you have seen the SVD in your linear algebra course or something like that. But what is SVD? Let's say we have a matrix. So we have a given matrix, and we could actually decompose this matrix to the form of U and diagonal matrix and V Hermitian. So again, in the case of real matrices, we have transpose instead of H in here, because VH means that just conjugate transpose. So yeah, and U and V in here, the property of U and V is that they are unitary. So what is this lambda in here? The lambda is the components of this is actually the eigen values of, so the lambda I is eigenvalue of x Hermitian x. So actually we call these singular values. We call these singular values of x. And what are the components of U and V? The columns of U, let's call them Ui, are eigenvectors of x Hermitian, and for the Vi, the components are eigenvectors of x Hermitian x. So they are left and right eigenvectors of x. So if we approximate x with x hat, then let's define the x hat in this way. So just note that we want to compress our data. So for this reason we defined x hat in here, which we want to approximate the x by x hat by using just k components in here. So it means that you know, each of these matrices has rank 1, so the sum of all these independent matrices have rank k. So this is rank k approximation of the matrix. And if we define the square error, it is the difference between the components of x and x hat. And it turns out that we could actually simplify this term to I from k to r minus 1, sorry, n minus 1 lambda I. So it is so much like PCA or KL transform that we talked about it. So it means that if you want to have the best approximation in Frobenius norm sense, so because this means that we just use the difference matrix and then use its Frobenius norm, means that we just square each of the elements of the square error of the error matrix. And so if we want to minimize the error in Frobenius norm sense, we could use SVD, k first components of SVD to have the best approximation. So it is much like PCA. So but the difference is that the PCA or KL transform is related to a single set of samples, but SVD actually related to ensemble of them. So I hope that it is clear now what is the difference between SVD and PCA, but they are closely actually related to each other. So I just introduced SVD in here. The next thing maybe that is interesting to you is that until now we learned PCA. So we know that PCA is a linear transformation because we see that we could apply that transformation on our data with something like this. But the fact that is sometimes, in fact, in many of times we have nonlinear data. Let's see an example of nonlinear data. So in this case we have absolutely nonlinear data, but it seems that they are actually separable in R2. So could we do anything to solve this problem? We know that in the formulas of PCA we just saw x Hermitian, so it was related to the correlation matrix. So when you see something like this or something like this in your formula, so in SVM we had something like this, if you remember that. In here you could think of kernel trick. So what was kernel trick? Kernel trick means that you could actually transform your data into high dimension and return back to your dimension, and so it seems that you applied a nonlinear transformation or running your algorithm on your data. So if you remember that in the SVM case, if we run SVM on this and we use RBF kernel, although SVM is a linear algorithm, SVM with kernel trick of RBF could get approximately, I think, completely and perfect performance on this data, because it transform the data into another space. In that space they are linearly separable, and then convert them back to the original space. So let's say just to see what happens when we increase the dimensions, to get some sense about it, let's say in here we just increase the dimension by 1. So we have x1 and x2, and we use x1 squared plus x2 squared as a third dimension. So if we plot the data in this space, we could see that now in this space these data are completely linearly separable. So in this data, if you have linear SVM, you could get perfect performance. You could apply PCA in here, and so on. So the fact is that when we want to use PCA, we could do the same thing in SVM that we did, and then actually we apply kernel trick and we get kernel PCA or KPCA. So in this case, maybe it is better a little to talk about the formulas. So when we apply the kernel phi, then we could write the average as sum of these. And just note that when you apply PCA, you should have 0 mean. Okay, your data should have 0 mean. Okay, and C is 1 over n, which C is actually covariance matrix, so it is phi. So these, when we apply phi, means that we increase, actually we apply our nonlinear transformation to the data. So the phi's are our kernel. Okay, now we want to obtain eigen values and eigen vectors in for this covariance matrix. So we want to solve this equation, which is the equation of eigen values and eigenvectors. So it turns out that we could write the V as sum over our data, actually our transformed data, with a scalar multiplication. So if we do a little mathematics manipulation, we end up with, and so using this, we end up with V is equal to phi xi dot V phi xi transpose. And just note that it is just a scalar. So the scalar in here, it seems that we just have a scalar in here because it is a dot product. So finding eigenvectors is equivalent to finding coefficients alpha I. So we need to solve this problem. If our kernel that we changed our and transform our data with that is k, then we need to solve this to obtain the coefficients, or in other words, we need to solve this problem for all j. And after solving this and obtain alpha i's, we could transform a new data x. So for new example, new data x, if we want to project that data on the space, we could actually write that as alpha ji k of x and xi. So in here you could see that actually it is not now very important to know much about these details. So but you should have that intuition about the kernel trick. So the same thing that we did in SVM to apply nonlinear transformation to our data, the same thing we could do this in here. So and the good news is that the Kernel Pca is implemented in a scalar, so you could use that. So in here we could see an example in a scalar. We could see that we have non-linearly separable data in here. It means that you could not have any line that separates between blue class and red class. So if you apply if you apply Kernel Pca in here, let us see the Kernel Pca. So you should define the kernel in here. So we saw that we have RBF, we have polynomial kernel. So in here, because the data have circular shape, we chose RBF in here. So we have RBF kernel in here, and then just fit transform, so the usage of the Pca is the same in here. So after projection by Kernel Pca, you could see that we have something like this. So actually they are now linearly separable in this space, so it is a very good news for us. And so for dimension reduction, you could use Kernel Pca when your data is actually not linear. They are not linearly separable, or they have not Gaussian distribution. You could use Kernel Pca, which is a useful tool for us when we are dealing with nonlinear data. Okay, the last thing that we want to talk about that today is ICA. We don't want to talk too much about that because actually it has a long story, but ICA, we just want to know about just the basics of ICA, or independent component analysis. So in PCA, what did we do? In PCA, we want to find a transform that could produce some features that are mutually uncorrelated. So this is the goal of PCA, to find a space that after the projection you have mutually uncorrelated data. But in ICA, we want to find some features that after the transformations, so we want to find a transformation, that after the transformation you have mutually independent data. So as you know, independency is much more stronger condition than uncorrelated data. So in here you will have much more stronger condition. And so this is actually the intuition behind ICA, to just know that it is something that is stronger than PCA and tries to find mutually independent features in comparison with PCA, that the PCA just want to find mutually uncorrelated data. So you guess that ICA is much more probably complex and harder than PCA. So one of the classic example of using ICA is to, in here you could see that, let's say you have some people, or in here it says that you have 3 microphones or 3 people that are talking to a microphone, and you just extract, you just see the mixed signal in here. So you just get one signal and you want to separate the audio of each person. So in this case, probably PCA cannot perform very well, because actually your signals are not related to a Gaussian process. So if you use ICA in here, you could see that ICA recovered something like this, this signal and the red signal and the blue signal. And if you see the true sources, also you have this one, which is related to this sinusoid, and so on. So ICA performs very well in here. But if you use PCA, as you could compare this to, you could see that it actually performs very poor in here. So ICA, you just have the idea about using ICA, and you could use that in scalar. So sometimes maybe it is good to try ICA. Actually, it is used for blind source separation. So in here we had 3 different sources that we don't know which person is for what signal. So we just want to separate the signal to assign it to the people, to different persons. So yeah, another classic example that I want to show you is, so we learned about ICA. It is just an example of using PCA, that how much it could be beneficial for us to use PCA. And so in here we have a classic example of eigenfaces and SVMs. So we want to recognize faces, and so the goal is face recognition. Okay, so this is a data set that, so we load the data set in here. Now if we apply PCA in here, if you apply PCA, then reshape the PCA components. So we know that PCA components means that the directions that we had. So now, because we have images, we just now first convert our images to vectors. Then we obtain some components that are related to eigenvectors. So for converting back them to the images, we reshape them to have some images. So it is very interesting that now if you see that eigenvectors, you could see, let me zoom out, zoom in here to have a better insight. Yeah. So as you could see in here, we will have some eigenfaces in here. So they are related to just eigenvectors, but because they were 2D, we just reshaped them, so we call them eigenfaces. So you could see that they are some kind of basis for the face space. So if you have, if you want to create a new face, you could see, for example, that you could just linearly have a combination of these faces, like 0.1 from this face, 0.2 from this face, and sum all of this to get some new faces. So this is the reason that we call these eigenfaces. So the cool things about this is now we could use this to recognize the data set. So actually we transformed our data in here, and also we transformed our test data in this space. Now we just need to create our SVM on just transform data. So now instead of having lots of pixels, so if you want to just train your SVM on the plain data, you will have lots of different pixels in here. So if you have 20 by 80 image, you will end up with, so let's do this in here. So if the image is 80 by 20 by 30, which is relatively a small image, then you will have, if you vectorize this, you will have 2,400 dimensions, which is a lot. And so this actually, when you apply SVM on this dimension, you probably will be prone to overfitting. You could try that. But if you apply PCA, then I just could get some eigenfaces. So I will end up with just 10 different directions. So I can reduce this dimension to just 10. Now you could apply PCA on this SVM on your 10 dimensions. So you will probably prevent overfitting in here, and your training performance and training time is much more faster in comparison with when you have lots of dimensions. So yeah, that's it. After that, you could train your SVM on your transform data and get the performance. We actually talk about the different metrics of performance, but for a rough measurement, accuracy is 85% roughly, so it is probably a good way to classify faces. And this is actually a classic method to face recognition problem. Yeah, I hope that actually you grasp the idea behind PCA. So it is so important using PCA in different problems could help you to reduce the dimension. And I hope this session was interesting for you, hopefully, and hope to see you in the next session. Bye.